Okay, so now I will present our next speaker. So Dr. Rauschenbeutel is a professor at the Humboldt University in Berlin and a researcher at the Center for Photonic Quantum Technologies. His research focused on quantum mechanically coupling light and matter on the surface of ultra-thin glass fibers. He has received the European Young Investigator Award from the European Science Foundation, a Marie Curie Excellence Award, and an ERC Consolidator Grant. He has also founded the Vienna Center for Quantum Science and Technology. Today he's going to present us a talk about correlating photons using the collective nonlinear response of atoms weakly coupled to an optical mode. Dr. Rauschenbeutel, the floor is yours.
Thank you very much, Viviana, for the kind introduction, and also thank you for the invitation. So let's start sharing my screen. That seems to work. And then start the presentation. And then the laser pointer. Okay. So, as Viviana said, my talk is on using a collective enhancement of nonlinearity of emitters that are only weakly coupled to an optical mode in order to realize strong photon-photon interaction. And before starting, I would like to thank the people who really did the work in the experiment. The experiment was still carried out at the Vienna University of Technology, and since then our group moved to Humboldt University in Berlin. And the two PhD students who worked on the experiment were Jakob Hinay and Adash Prasad, and the experiment was supervised by my senior co-workers, Philipp Schneeweiß and Jürgen Volz. And there was also a very fruitful theory collaboration with the universities of Hanover and Copenhagen, with Clemens Hammerer, Sahand Mamodian, and Anders Sørensen. So as I said, the talk is on strong photon-photon interactions, and I guess I do not need to spend a lot of time to motivate why strong photon-photon interactions are very useful for quantum nonlinear optics and for quantum information processing. For example, you can realize photon-photon gates in cavity quantum electrodynamics, but they're also interesting for quantum simulation. Now my computer stalled. That is worrisome. Oh, okay. Now something happens here. Okay, it seems to work. So it's also very useful for quantum simulation. For example, if you send photons into a nonlinear medium and increase the interaction strength, it may result in some repulsive interaction where the photons start to minimize their overlap indicated by this yellow area here. And if you then analyze the intensity autocorrelation function, it may exhibit a minimum at zero time delay, meaning that the photons are kind of crystallized in our medium for sufficiently strong interactions. So the typical approach for achieving such a strong photon-photon interaction is to strongly couple light to a quantum emitter and exploit the inherently nonlinear response of the latter. And this can be done, for example, by using high finesse optical cavities. The interaction can also be mediated, for example, by dipole-dipole interaction among Rydberg atoms. Or you can, for example, place your emitter into a waveguide where the light is strongly confined in the transverse direction, and thereby the photons sort of cannot avoid our emitter. And if we now want to enhance and control the fidelity of this photon-photon interaction, then what you need to do is to increase the light-matter coupling strength and to reduce the dissipation. And this can be achieved, for example, as I said, by strongly transversely confining the light, as here is in some photonic crystal waveguide. You have to reduce the propagation loss, or if you work with resonant structures, have to increase the quality factor of the resonator, as here for our for some whispering gallery mode resonator. And finally, you can also tailor your quantum emitter to exhibit particularly strong dipole matrix elements, and so to increase the Rabi frequency. But eventually, it turns out that for all these schemes here, dissipation still is your worst enemy, because dissipation causes photon loss and thus blurs out the photon-photon nonlinearity. And the approach of the work that I will be presenting now is based on the, let's say, topic, if you can't beat them, join them. Okay, so let's make dissipation if it's no longer our enemy, but our friend. And the photonic or nanophotonic platform that we use for these experiments is a two-color nanofiber-based atom trap, where atoms are trapped in the evanescent field surrounding a sub-wavelength diameter optical fiber. So here what we do is to send through such a very thin dielectric waveguide red and blue detuned light field with respect to this D2 transition of cesium. And the red light field then exerts an attractive force that attracts the atoms to the waveguide, whereas the blue detuned light repels the atoms from the waveguide. And since this happens in the evanescent field part surrounding our waveguide, and the decay length of the evanescent field is proportional to the wavelength, it turns out that the blue light is more tightly bound to our nanofiber than the red light. And this means that when an atom approaches the nanofiber from a distance, it first sees the attractive force of the red light-induced potential, and then when it approaches the fiber further, it starts to feel the repulsion of the blue. So here I plot actually the potential energy of the cesium atom approaching our fiber as a function of the distance from the nanofiber surface. And what you see is that the sum of these two forces, if powers and detunings are appropriately chosen, which is indicated by this black line, can feature a potential minimum at a distance of about 200 nanometers from the fiber surface. And so atoms which are trapped here are also coupled to further light fields which now propagate through the fiber via their evanescent field. So this shows us that we can have some radial confinement of the atoms. We would, however, like to localize the atoms in all three dimensions, and this can be achieved. For the axial direction along the fiber, we simply launch the red detuned light field from both sides and create a red detuned standing wave. So this means that we now have actually still radial trapping, but in the axial direction, the red potential is modulated, and we have actually here trapping periodically along the fiber with a distance of about 0.5 micrometer between adjacent trapping sites. And now, given the cylindrical symmetry of our waveguide, one might now be led to think that we end up here with toroidal traps around the fiber. However, what breaks the cylindrical symmetry is the linear polarization of our trapping light fields in conjunction with the strong guiding of our waveguide, which exhibits a strong index of refraction jump between the glass here and the air or vacuum surrounding the waveguide. And in this case, for a linearly polarized light field in the plane of polarization, you have about 3 times higher evanescent field intensity than in the plane orthogonal to the plane of polarization. So this means that if we now launch the red and blue detuned light fields linearly polarized and crossed in their polarization, we have more red detuned light field here and more blue detuned repulsive light field here, which means that we also confine our atoms in the azimuthal direction. So plotted all together, our potential looks as shown here. Here I plot the potential, equipotential surfaces of 40 microkelvin and 125 microkelvin above the trapping minimum. And actually, these light-induced potentials are so confining that a so-called collisional blockade takes place, which limits the number of cesium atoms that can be loaded into each trapping site to at most 1. And this mechanism then saturates in the sense that we either have 0 or 1 atom per trapping site, and we end up with a filling factor of 0.5. So here the distance of the atoms from the fiber surface is about 250 nanometers, and the trap frequencies are in the 100 kilohertz range in all 3 dimensions, which means that the atoms are localized in all 3 dimensions to much better than the optical wavelength. And so while we were the first to demonstrate such a 2-color nanofiber-based atom trap, by now there have been, are, and will be many more of those, and maybe I forgot somebody here, and the field even grow further. So as I said, if we now launch light through the fiber while atoms are trapped in these one-dimensional optical lattices above and below the nanofiber, light will be absorbed. And the absorption can be characterized by the optical depth, which is the negative logarithm of the transmission. And each atom removes a bit of the power propagating through the waveguide. So we can define an optical depth per atom. And in our case, this optical depth per atom is in the range of 0.01 to 0.1. Typically in nanofiber-based atom traps, you can trap between 1,000 and maybe 10,000 atoms. And if you then compute, starting from the optical depth per atom, the total optical depth, you just multiply the optical depth per atom with the number of atoms, and you end up with a total optical depth of 10 to 1,000. Of course, when writing down this equation here, I was assuming that the total transmission through the fiber is actually given by the transmission past 1 atom to the power of the number of atoms, meaning that we assume that Beer-Lambert law applies. Okay. Now, if we measure the transmission as a function of the tuning of the laser, we then see that indeed we can reach high optical depths. So here I plot the transmission through our fiber with an ensemble of atoms trapped along the fiber as a function of probe laser detuning. And the blue dots are the experimental data. And you see that indeed we have here some completely opaque sample, which over a range of 10-20 megahertz has basically vanishing transmission, and you can fit this with a saturated Lorentzian absorption profile, which is this red line here, and extract the optical depth from this fit. And for example, in this case here, we find an optical depth of 32. And if you heard me give talks about this system, then probably you also heard me saying things over the past 10 years, like saying, if we have an optical depth of 32, this means that the transmission through our system is only e to the minus 32. And it turns out that this is not quite as simple if you look at it in detail. And we became aware of that when a paper appeared by Clemens Hammerer and Sahand Mahmoodian and Anders Sørensen and other co-workers, where they considered the transport of photons through such a waveguide, which is weakly coupled to an ensemble of emitters, and showed that actually there photons may become correlated, and things get somewhat more interesting than what I was just highlighting. So in order to understand what's happening here, we have to briefly revisit resonance fluorescence. When we scatter resonant light off a 2-level atom in the limit of vanishing saturation, as we already saw in the last talk by Kai Müller, you actually only expect elastic scattering, which means that since energy is conserved, the spectrum of our scattered light is basically a carbon copy of the laser spectrum, and the line width here can be as narrow as the laser line width. However, of course, this is only for vanishing saturation, and in an experiment you always have a finite, even if it's a weak saturation, which means that there's also inelastic scattering. This is exactly this process that also Kai was discussing about in his talk. Inelastic scattering, which actually corresponds to such a 4-photon process. So meaning that a pump photon here is absorbed, and then before the actually atom returns to the ground state, a second pump photon arrives, such that you can actually emit a red detuned photon, for example, here, absorb the next pump photon and emit a slightly blue detuned photon. And actually, if these two photons here, red and blue detuned, are emitted within the lifetime of the excited state, then they can be spectrally broader than the laser spectrum and actually give rise to this so-called incoherent background, in addition to this elastic peak here. If we call this incoherent background, then maybe I should stress that it's not exactly just single photons which are broader in frequency than the laser, but actually we see that here we have to conserve energy at the end of this 4-photon process, meaning that these broader photons are always emitted in pairs. Okay, so here we have actually in this incoherent background, it's rather correlated photon pairs, which are energy time entangled such that the sum of their energies equals the sum of two pump photons. Okay. And now let us consider the absorption of light that propagates through an ensemble of atoms along our waveguide, if this nonlinear process here is also taken into account. Okay, so our nanofiber is actually realized as the waste of a tapered optical fiber. So this is a step index fiber which has been heated and pulled such that the waste has a diameter of about 400 nanometers, and it's here that we trap the atoms, and then we can just launch light into our standard fiber, and it's adiabatically matched to the nanofiber guided mode and back again. And we can then analyze the light that is transmitted past the atoms. Okay. And this is done very efficiently, this adiabatic mode transformation. We can have more than 99% transmission from one end to the other of this tapered fiber. And another important technical aspect is that we can have very low fiber fluorescence. Remember that we have strong trapping light fields in here, which may cause fluorescence also at the resonance wavelength of the atoms. But actually this fiber fluorescence can be suppressed sufficiently using also bandpass filters here, that we can actually analyze light here in a Henbury-Brown twist configuration, and we can be sure that the light that we see here predominantly comes from the atoms, so has interacted with the atoms and is not just background fluorescence. The probe light that we launch into our fiber is resonant with the cycling transition, the D2 line cycling transition of cesium, and the power of light that we launch into the fiber is only about 2 picowatts, which means that we have a saturation parameter much smaller than 0.02. So here one would, at a first glance, consider that everything should be in the linear regime. And just one brief remark is that the probe light that we launch into the fiber is linearly polarized, meaning that the nanofiber guided mode is a so-called quasi-linearly polarized mode, which gives rise to direction-dependent light-matter interaction. This is only for the experts here. It does not really play a significant role for the mechanism that I am presenting. So let us now look in detail at what happens here in our nanofiber-based atom light interface when this resonant light field propagates through the ensemble of atoms. And let us only look now at the 2 photon component of this probe light. Okay, so the 2 photon component has a spectrum of the laser line width initially, and then hits one atom after the other. And when now meeting one atom, there's actually three things that can happen. The two photon component can be absorbed in the sense that one photon is scattered out of the waveguide and it's no longer a two photon component. It can simply be transmitted past the atom so that it's still there after the atom. But there's also this weak but finite probability for this two photon scattering event to take place here, where we generate this correlated two photon state, and this correlated two photon state, however, has, as we said, a broader spectrum than the pump light here, which has the laser line width. The spectrum here is as broad as the atomic transition. And that means that the correlated photon pairs that are generated here experience reduced absorption by the rest of the atoms along the waveguide here, okay? And then there is another very important aspect of this geometry here, which is that the two photon, this correlated two photon state is generated by forward scattering, and that means that the amplitude of two photon scattering from all the atoms along the waveguide interfere constructively. So this means that the two photon forward scattering process that we consider here is collectively enhanced, while at the same time the unscattered two photon component experiences linear loss at each atom and is thus subject to exponentially decreasing power along the waveguide with the number of atoms, okay? So if we then look at the spectrum of the light that exits our waveguide here, it will be composed of our laser line, which is exponentially suppressed due to linear absorption, and it is composed of this incoherent background, which consists of correlated photon pairs. And the spectrum of this incoherent background, we said, is actually just a Lorentzian in the process of the two photon scattering. However, this Lorentzian has then been filtered by the remaining atoms with the same Lorentzian filter function, and that then results in the spectrum, which has a hole in the middle here where the correlated photon pairs are absorbed by the remaining atoms, but we still have in the wings where our remaining atoms absorb less efficiently some spectral features here of our incoherent background. And if you look at the power that is contained then in this correlated photon pairs that are transmitted past all atoms because they're spectrally broader, interestingly, the prediction is that there's actually only a power law decay of the power transmitted through the waveguide because of these correlated photon states. So that means that here, Beer-Lambert law does not apply in the sense that when you send in a certain power into our waveguide, which is not saturating our atoms, the transmitted optical power does not scale exponentially with the number of atoms, but only polynomially. So it's actually 1 over the number of atoms to the power of 5 half. So, however, we will now concentrate more on analyzing the photon statistics of the light that propagates along the waveguide. Okay, so of course the photon statistics before the light meets the atoms is just that of laser light, meaning that G2 as a function of waiting time will be just flat and equal to 1. But now when we hit the first atom, we create the scattered two photon component, and this scattered two photon component, since it's a resonant scattering process, involves a 2 pi phase shift with respect to the unscattered two photon component. So I try to indicate that here by the out of phase of the wave that I indicate here for the unscattered to photon component and the scattered to photon component. And this means that these two components, the unscattered and scattered to photon component, interfere destructively. So if we now are in the low optical depth regime, say just after the first atom, loosely speaking, then the amplitude of the scattered component is smaller than the amplitude of the unscattered component. So the destructive interference then leads to some slight anti-bunching at 0 time delay. However, if I further propagate along the waveguide, because of the collective enhancement and reduced absorption of the scattered to photon component and the exponential loss of the unscattered to photon component, at some point, the two components will have the same amplitude. So this happens for some critical optical depth. And in this case, the interference is perfectly destructive, and we expect perfect anti-bunching, where the probability of having two photons arriving at the same time at our detector vanishes. And then finally, if we go to very high optical depth, due to the exponential loss, our unscattered to photon component is completely damped away, and we're only left with the scattered to photon component, which reduces less loss. And this means that only the scattered to photon component survives, and we expect strong bunching here. So let us now look in our experiment if we can observe this modification of the photon statistics as a function of number of atoms. So we measured here the second order correlation function at the exit of the fiber for atom numbers reaching mean atom numbers trapped on the nanofiber ranging from 100 to about 200. And what you see is that indeed for 100 atoms along the nanofiber, we have slight anti-bunching here. So the blue dots, or the blue line, is the experimental data, and the red line is the theoretical prediction. And when we increase the number of atoms, we observe here for 160 atoms pronounced anti-bunching. And then for 180 atoms, we start to see some onset of bunching. And for 200 atoms, we have very pronounced bunching here. So just note that I change from panel A and B to C and D the scale of the vertical axis, which goes up to 2 here, whereas goes up to 10 here. So you see that here for 200 atoms, we really have pronounced bunching of our light exiting the nanofiber-based atom-light interface. So as I said, the blue line is the experimental data, and if we convert the number of atoms that were present here into optical depth, the optical depth ranges from about 3 to 6. And the orange line is actually a theory prediction which takes our experimental parameters into account, and also our main experimental imperfections. And the biggest experimental imperfection is actually that the number of atoms that we trap along the nanofiber is not determined very precisely here. So we have some average mean atom number that for this measurement here. However, there's also a variation in atom number, which leads to some smearing out of our signals. Actually for these theoretical predictions, we assumed an atom waveguide coupling strength of about 1%, and this has been derived from fitting the value of G2 at 0 time delay as a function of the optical depth, with only this coupling strength beta as the fit parameter. And then, as I said, you see clearly bunching and anti-bunching, and let me just show you this fit of the 0 time delay G2 versus optical depth. So here I plot G2 of 0 as a function of optical depth, and you see that we do get some pronounced anti-bunching. The blue dots are the experimental data, and again the red line is the orange line is our theory prediction accounting for the experimental uncertainty, and only has the coupling strength beta as the fitting parameter. And then finally, for comparison, I also show this green dashed line here. which is the theory prediction if there was no uncertainty in the atom number and the same coupling strength beta. And then you see that indeed this signal goes to 0 for critical optical depth of about 6. So here the strongest antibunching that you observed in the experiment was observed for 160 atoms. And bunching starts for about 180 atoms. And to see this, I change here from a linear scale to a log scale. So in order to be able to show you that indeed in the high optical depth regime, we do get pronounced bunching of the light propagating through the fiber up to experimentally observed a value of 20 for G2 of tau equals 0. Okay, so that is for an optical depth of about 8. So what I showed you is that an ensemble of weakly coupled emitters, in our case atoms, can be indeed realized to strongly correlate photons and to realize many body states of light. And it turns out that the underlying dynamics is some intricate interplay between a weak optical nonlinearity. So the atoms each atom is only weakly coupled to our waveguide. However, the nonlinearity is collectively enhanced. And we also need the finite dissipation, which suppresses our pump light exponentially and thereby allows us to have this perfect destructive interference between the scattered and unscattered two-photon component. So where can this lead to? First of all, it is of course well known that a collective enhancement can be used to enhance the interaction of light with an ensemble of atoms as compared to the single atom case. But to our knowledge, here is the first time that it has been demonstrated that such a collective enhancement can actually be applied to enhancing a nonlinear interaction and thus to enhance non-Gaussian operations. And this significantly broadens the range of possible applications, for example, in the framework of quantum information science. For example, we believe that our approach is fundamentally new and can help us to realize a single photon source using weakly coupled emitters, so where the source can outperform a source based on a single emitter of the same coupling strength. Let's say you have a spectral range where you don't have a single emitter which is strongly coupled to a cavity or a waveguide, but only weakly coupled emitters are available, then our approach would allow you to realize a much higher output rate of single photons than the individual emitter that is weakly coupled to the optical mode. So with this, I thank you for your attention, and I also thank the funding agencies for financing this work.
Okay, many thanks for that beautiful talk. We will now move to the question and answer section. Dr. Weinfurter, the floor is yours.
Okay, Arno, how long are the atoms trapped along the fiber is the first question.
How long are they trapped? So the atoms are actually, so our scheme was based on some interleaved cooling and probing, so to keep the atoms for the longest time and to have the best, let's say, use of the trapped atoms. And in this case, if we actually Doppler cool the atoms in between our probing sequences, the atoms are kept for about a second before being lost.
Okay, and could you reach strong coupling of a single atom to the light in the fiber as well? What would be the conditions then?
So here, what counts is the transverse confinement of the light field. You have to compare, let's say, the mode diameter with the interaction cross section, and in our case, this is limited by the index of refraction of our fiber. And if you put the emitter on the nanofiber surface, then the maximum value that you can hope for is about 30, so 0.3 beta. Okay, and if you want to go beyond that, different strategies exist. First, you could use higher index waveguides where you can further confine the light in the transverse direction. Or you could then use some resonant structure. So this is also an approach we realize in our group, where we now have a fiber loop. So it's a fiber ring that has a tapered fiber section. And when we now couple the atoms to this nanofiber waist, then we are in some, let's say, moderate finesse resonator. But since the coupling per atom, even in the propagating case, is already sizable, you can then reach the strong coupling regime. So this has also been demonstrated by Takao Aoki experimentally.
Okay. What determines actually this filling factor?
The filling factor is determined by the so-called collisional blockade effect. So this is an effect that has been studied first by Philippe Grangier in 2000, I think. It's the following: when a single atom is loaded into this tiny optical potential, and in the presence of this near resonant cooling light that now tries to cool another atom into the potential, when the second atom enters the potential, there is a photochemical reaction taking place because of the high probability of the atoms being close by, which excites the atom, for example, to some repulsive molecular potential, and then causes some exothermal reaction, which makes both atoms leave the trap. So in that sense, you're permanently projecting onto 0 or 1 atoms in the trap, and as soon as the second atom enters, you're again down to 0. And there is actually, for a certain parameter range, this process saturates, meaning that there's a plateau of filling factor of 0.5 because of that. So that limits the filling factor. If you wanted to have higher filling factors, it has been demonstrated that such blockade effects can also be used to limit to load exactly 1 atom per well, but that involves very fine tuning of the laser frequencies and suitably chosen laser frequencies such that the collision only expels 1 atom from the trap, so that there's always only 1 atom in the trap, and the second one enters and leaves again, or one of the 2 leaves, but there's still 1 atom remaining. This has been demonstrated experimentally.
Okay, a last question concerns the interference. I mean, could it be also constructive between the interference between scattered and the pump rate?
So as I said, this scatter to photon component comes from some resonant scattering process where 1 photon is absorbed and re-emitted, whereas the second just passes by. And it's this actually absorption and re-emission of a single photon that induces a pi phase shift on the global scatter to photon state. So I think that here it's actually similar in the your question in the linear regime would be similar to asking, can I convert absorption into amplification? And I think if you don't pump the system, you can't. So I mean, basically, the pi phase shift gives rise to a reduction of the 2 photon probability in that sense, and I don't think that you can easily change that.
Okay, thanks a lot for the time being. Yeah, I guess we can meet afterwards in the meeting room for all the more questions.